Good afternoon, students. So, in our previous class, I have explained to you about the performance analysis of a DSBSC system and AM method, right? So, in today's class, we will see the performance analysis of the remaining methods. One second. So first we will see the performance analysis of a SSB-SC system. It is the block diagram of a SSB-SC system. So here we are having a channel and the input to the channel is a SSB signal which is represented by S of T, and also noise which is a white noise N of T, and that signal plus noise N of T plus S of T is given to the narrow band pass filter, and the output of a narrow bandpass filter is S of t plus N of t. So it is given to the multiplier. So and we're also giving cos 2 pi fct, which is a carrier signal. So that multiplier output is given to a low pass filter. And finally, we will get output as a S naught and N naught. So it is at a receiver side. Now we will see the performance analysis. So to find the performance analysis, we have to calculate the four parameters, right? They are input signal power, input noise power, output signal power, output noise power. So we'll calculate one by one four parameters, and then we'll substitute all those four parameters in our equation. So first we will see the input signal power. So input signal power means I'm representing with S suffix I. So it can be written as AC by 2 cos 2 pi FCT into M of T plus or minus AC by 2 sin 2 pi FCT into M cap of T. So in next step, I'm writing it as AC by 2 cos 2 pi FCT. So in place of M of T, I'm just writing it as AM cos 2 pi FMT plus or minus AC by 2 sin 2 pi FCT. So in place of M cap of T, I'm writing AM sin 2 pi FMT. So in next step, I'm taking AC AM by 2 as a common. So it will become as AC AM by 2 into, so what are the remaining parameters in first term? Cos 2 pi FCT into cos 2 pi FMT plus or minus. So what are the remaining parameters in here? In the second term, sin 2 pi FCT, sin 2 pi FMT. So from the trigonometric formulas, we know the formulas, right? Cos A, cos B plus or minus sin A, sin B means we can write it as a cos of A plus or minus B. So I'm writing it as AC AM by 2 into cos of 2 pi FC plus or minus FM into T. So we know signal power means we need to consider the power formula amplitude square by 2. So I'm just writing SI is equal to amplitude square by 2. So here the amplitude is AC into AM by 2. So amplitude square by 2 means AC into AM by 2 whole square by 2. So it becomes AC square AM square by 8. So that is the input signal power. Now we will calculate, okay, AC square by 4 into AM square by 2. So in place of AM square by 2, I am just replacing it with a P. So power means amplitude square by 2 of a modulating signal. So I'm just replacing AM square by 2 with the P. So input signal power is equal to AC square by 4 into P. Now we will calculate the input noise power. So input noise power Ni is equal to integral SW of F into dF. So we can represent it as integral minus omega to omega N naught by 2 d omega. So we can write it as by substituting the upper limit and lower limit. So we know upper limit minus lower limit means it becomes N naught by 2 into 2 omega. So input noise power is equal to N naught into omega. And now we will find now output signal power. So at the receiver side, the input to the product modulator is a SSB signal as well as a noise. So we can write it as S naught is equal to AC by 2 cos 2 pi FCT M of t plus AC by 2 sin 2 pi FCT M cap of t plus noise N of t. So in the next step, I'm writing a noise in terms of in phase and quadrature components as AC by 2 cos 2 pi FCT M of t plus AC by 2 sin 2 pi FCT M cap of t plus here I am representing a noise n of t in terms of in phase and quadrature components as ni of t cos 2 pi fct minus nq of t into sin 2 pi fct. I explained this derivation in the previous classes. So here we are having a carrier signal cos 2 pi fct. So I'm just multiplying the whole equation with the cos 2 pi fct. So I have written the same equation and I'm just multiplying with the cos 2 pi fct. So then what it becomes? AC into m of t cos square 2 pi fct plus ni of t cos 2 pi fct minus nq of t sin 2 pi fct cos 2 pi fct. Then I'm just writing it as from the trigonometric formulas cos square 2a is equal to 1 plus cos 2a by 2. So we can write it as AC by 2 into 1 plus cos 4 pi fct by 2. So why I'm writing like this means from the trigonometric formulas cos square 2a is equal to 1 plus cos 2a by 2. So I'm just implementing that formula here into m of t plus AC by 2 m cap of t into sin 4 pi fct by 2 plus ni of t into 1 plus cos 4 pi fct by 2 minus nq of t into sin 4 pi fct by 2. So in next step, we will just write the individual terms, right? Like here we are having a AC by 2 into 1 plus cos 4 pi fct by 2 into m of t, right? So I'm just writing the individual terms. If I multiply this, what I will get? Look at the first term. If I multiply, what I will get? AC by 2 into m of t plus AC by 4 cos 4 pi fct into m of t. Like that, I'm writing the individual terms in the next step. So next, we are passing this signal through a low pass filter. Then what happens? Low pass filters allows the low frequencies only, and it attenuates or rejects the high frequency signals. So at the output of a low pass filter, we will get the only low frequency components. So here the low frequency components are AC into m of t by 4 plus ni of t by 2. So they are the low frequency components. So it is having the output signal power and output noise power. So to calculate the output signal power, we will take the first term. So now we will calculate the output signal power. S naught is equal to, from the above equation, we will write AC into m of t by 4. So m of t means message signal. We can write it as a am cos 2 pi fm of t. I'm just replacing in place of m of t. So AC by 4 am cos 2 pi fm of t. And in next step, I'm writing it as, so power means amplitude square by 2. So I'm just writing it as AC square AM square by 4 whole square. So then what happens? It AC square into AM square by 16 into 2. So by 2, amplitude square by 2. So first amplitude square by 2. So in place of AM square by 2, we can write as a P. So output signal power is equal to AC square by 16 into P. Next, output noise power. Here, N naught is equal to Ni of T by 2. So why I am writing like this means from the equation. Look at the here. Third step. After passing to the low pass filter, we are having AC into M of T by 4 plus Ni of T by 2. So from that equation, we have to calculate the output signal power and output noise power. So I'm taking second term for the output noise power. So it can be written as N naught is equal to Ni of T by 2. So here, E of N naught is equal to 1 by 4 Ni square of T. So the average power can be calculated by N naught into Bt. So here Bt means nothing but a transmission bandwidth. And N naught is equal to 1 by 4 into N naught into Bt. So N naught by 4 into here, the transmission bandwidth is omega. So we can write it as N naught is equal to N naught into omega by 4. So that is the output noise power. So up to now we have calculated the 4 parameters, right? Input signal power, input noise power, output signal power, and output noise power. Now we have to substitute all those formulas in this figure of merit. If you observe here in the figure of merit, so I'm just writing the all 4 parameters and then they'll cancel to each other. Then we will get output the figure of merit as a 1. So it is the formula for the noise performance analysis of a system. So figure of merit formula is output SNR by input SNR. That's why we're substituting here the 4 parameters. So figure of merit means output SNR by input SNR. So output SNR means S naught by N naught out Input SNR means SI by NI. So I'm substituting like this. Now we will see the performance analysis of a FM. So here we have seen the performance analysis of a SSB-SC. Now we will see the performance analysis of a FM. So it is the performance analysis of a FM. Here we can see the block diagram. So the block diagram will consist of a summation. So the inputs are SFM of t, which is a FM signal and noise signal N of t, and that output is given to the band pass filter, and the output of a band pass filter is given to a discriminator, and discriminator output is given to the envelope detector. The envelope detector output is given to the low pass filter. Now we have to calculate the 4 parameters. So to calculate the figure of merit, so simply I'm writing it as a FOM, figure of merit. So figure of merit means output SNR by input SNR. So to calculate the figure of merit, we have to calculate the 4 parameters: output noise power, output signal power, input noise power. So first we will calculate those. So first output noise power P N naught is equal to integral minus W to W F by AC square into N naught into DF. So we can write it as P N naught is equal to N naught by AC square into F cube by 3 W minus W. They are the limits. So what happens next? N naught by AC square into 2W cube by 3. So that is representing as the equation number 1, output noise power. Now we will calculate the output signal power. So the output signal power can be calculated from KFM of T. So P S naught is equal to K F square of P. So that is equation number 2. So SNR output means signal power to the noise power, output signal power to the output noise power. So from the equation 1 and 2, we will substitute those two, output signal power and output noise power. So from equation 1 and equation 2, I am substituting those two. Then we will get SNR output as N naught by AC square into 2W cube by 3 by Kf square P. So what happens? This equation will become as 3 into Kf square into P AC square by 2 N naught into omega cube. So that is equation number 8. So which is a SNR output. So to calculate the SNR input, we have to calculate the input signal power and input noise power. So we know, we have discussed so far about the input signal power. So input signal power means nothing but amplitude square by 2. So PSI is equal to AC square by 2. Next we will calculate the input signal power. So it is input noise power, it is input signal power. It is input noise power. There is some mistake. Fourth one is input noise power, not a signal power. So PNI is equal to N naught W. So from the equations 3 and 4, we have a signal power and noise power. So from this equation, we have a signal power. From this equation, we have a noise power. So to calculate the SNR input, we just substitute here. Then it becomes A cube by 2W N naught. So that is equation number 9. So we have SNR output and we have SNR input. So to calculate the figure of merit of a FM, we have to substitute those two values here. So then it becomes, by substituting, FOM means figure of merit is equal to 3 into K square P AC square by 2 N naught omega Q W cube by AC square 2 W N naught. So then it becomes, by cancelling the terms, 3 into Kf square P by W square. So to match this AM modulation, we can use M of T cos omega T. Then the signal power P is equal to 1 by 2 and W is equal to FM. So the figure of merit for a FM, FOM represents figure of merit. FM means FM signal. So the figure of merit of FM signal can be written as 3 Kf square by FM square into 1 by 2. Why? Because in place of P power, I'm just substituting 1 by T. In place of W, I'm just substituting FM. It can become 3 by 2 into Kf by FM whole square. So in place of Kf by FM, I'm writing it as a beta. So the FOM ante the figure of merit of a FM is equal to 3 by 2 beta square. So that is the performance analysis. So for the single tone modulation, KF by FM. When you compare the single tone FM with the AM, so what happens? So if you compare those two, it becomes as a 3 by 2 beta square greater than 1 by 3, then what is the beta value? Root 2 in root 2 by 3. So approximately this value is equal to beta is greater than 0.471. The modulation index beta is greater than 0.47 will be beneficial in terms of a noise cancellation. This is one of the reasons why we prefer the WBFM over the NBFM. WBFM means wideband FM, NBFM means narrowband FM. So I have discussed in previous classes WBFM and NBFM. So they are classified based on the modulation index. And last one, we will see the PM in the presence of a noise. So input is a SPM of T, phase modulated signal, and we are giving a noise, and the output is given to the band pass filter, and the output of a band pass filter is given to the PLL. PLL means phase locked loop, and that output is given to the integrator. Integrator output is given to the low pass filter, and finally we will get the output. So here also we have to calculate the 4 parameters: input signal power, input noise power, output signal power, output noise power. So to calculate the input signal power, SPM of T is equal to AC cos into 2 pi FCT plus RPM of T. So input signal power means amplitude square by 2. So here the amplitude is AC. So I'm just writing it as a AC square by 2, which is amplitude square by 2. That is input signal power. To calculate the input noise power, from the white Gaussian noise, we can write it as a Ni is equal to N0 by 2. So the bandwidth is 2W. So I'm just writing N0 by 2 into 2W. Why? Because N0 into bandwidth, noise into bandwidth. So it becomes 2 gets cancelled. We will get N0 into W. That is input noise power. Now we will calculate the output signal power. So we can write it as P of T is equal to 1 by 2 by RPM of T plus 1 by 2 by AC NQ of T. So output signal power means nothing but amplitude square by 2. So I'm just writing it as 1 by 2 by RPM of T whole square by 2. So here 2 is missing here. R square P M square of T by 4 pi square. So we can write it as 1 by 4 pi square RP square into P. So that is the output signal power. And now we will see the output noise power. So output noise power can be calculated. N0 is equal to 1 by 2 pi AC NQ of T whole square. So it becomes 1 by 4 pi square AC square N square Q of T. So we can write it as, in place of NQ of T, we can write it as a N0 into bandwidth. So bandwidth means 2W. So 1 by 4 pi square AC square into N0 into 2W. So S0 by N0 becomes RP square by P by 4 pi square into 4 pi square AC square by N0 into 2W. So 4 pi square gets cancelled. We will get RP square P AC square by N0 into 2W. So to calculate the figure of merit, we have to substitute the 4 parameters: input signal power, input noise power, output signal power, output noise power. So by substituting all these values, and here I'm representing M of T as a AM cos omega MT. So power is equal to AM square by 2. So figure of merit can be written as half RP square AM square. And FOM can be, RPM can be written as a beta. So half beta square. That is the figure of merit of a FM signal. Sorry, PM signal. That is the figure of merit of a PM signal. So that is for the today's class. So in today's class, we have seen the figure of merit of a SSBSC and PM and FM. So these are the performance analysis of a various system. Thanks for watching.